In this screencast, we'll look at the reductive amination reaction, which is a strategy to take an aldehyde or ketone, condense it to an imine or enamine, then reduce it and form a new amine. So let's go ahead and we'll start with, a pretty straightforward case where we're going to use ethanal. Again, that's an aldehyde. The name ends in Al, so that's the parent functional group is an aldehyde, ethanal. We're going to condense that with ammonia. So we can consider ammonia a primary amine. So from our prior screencast, we have an aldehyde plus a primary amine that's going to give us an imine. And so remember, an imine is a nitrogen variant of a carbonyl, for example. So you have a carbon-nitrogen double bond. So as we saw with carbonyl-containing compounds that we can reduce them, we can also reduce imines. So we're going to add the elements of H2 across that pi bond, and that's going to result in an amine. So we have the imine formed, and in this case we're going to treat with hydrogen gas and then a nickel catalyst. And so when we do that, we're adding the elements of H2 hydrogen gas across that pi bond. And so our product is now an amine. And so this would be ethylamine. And so that's a review of amine nomenclature. You have the alkyl group that's bonded to the amine. So ethyl, it's a 2-carbon unit, ethylamine. So what this process or strategy, reductive amination, again, we're starting with a carbonyl. We're condensing that with an amine to form an imine, and then we're reducing that pi bond to form a higher order amine. So in this example, we're starting with ammonia, so NH3, and then we're actually adding an alkyl group on it. So we're forming a primary amine. But notice now we go from 3 hydrogens to 2 hydrogens and then an alkyl group. So let's look at another example. And so we'll start this one with this ketone. So this is propanone. So the ketone ending ends in ONE. That tells you it's a ketone. Let's go ahead and condense this with a primary amine. So this is methylamine. So carbonyl plus primary amine is going to give us an imine. So here's our imine. Now in this example, we're going to do a different set of conditions for the reductive amination. So we'll use as the reducing agent lithium cyanoborohydride. So that's a new reagent, lithium cyanoborohydride. So we've seen like sodium borohydride, This is just using a different metal here, so lithium is the cation. And the cyano group is replacing one of the hydrides, so we don't have 4 hydrides, we have 3. And so this is just to affect the reducing ability of the boron. These reactions are actually run, interestingly enough, in the presence of an acid. So trifluoroacetic acid, and that brings the pH to about 4. And so for a solvent, we can use tetrahydrofuran. And so again, notice in this top case, there's H2, HH. Those are where the elements of hydrogen come from. So under these conditions, essentially what happens is the acid will protonate the imine, and then the reducing agent provides the other hydrogen that adds to that imine. So let's go ahead and draw the intermediate that's formed in this process. So we add 1 H through the trifluoroacetic acid. And so the counter ion is just the CF3CO2 minus. So again, all we did is a proton transfer. This lone pair abstracted that hydrogen. We formed this species, which is called an iminium ion. And so now that is activated for the lithium cyanoborohydride to attack. So I'll draw this H. So there's our reagent. I'm going to show that red hydride being delivered. So there's where you get your elements of H2, one from the hydride reducing agent, one from the acid. And so now, if you notice, we started with a primary amine. Now we end up with 1, 2. This is a secondary amine. So we would name this according to the substituents bonded to it. So we have 1, 2, 3. We have an isopropyl group, and we have a methyl group. So we would say this is isopropyl methyl amine. So notice in this process of reductive amination, if you're starting with a primary amine, you end up with a secondary amine. So as you can project, if we start with a secondary amine, we'll end up with a tertiary amine. So let's start a new slide and look at one of those cases. So let's go ahead and start with, say, cyclohexanone. And we're going to condense that with pyrrolidine. And that's a secondary amine. So remember, when you're starting with a carbonyl containing compound, aldehyde or ketone, and you have a secondary amine, in this case you do not form an imine, but rather you form an enamine. So there's the enamine. So alkene, that's the ene, and then there's the amine, so enamine. Now we'll use our reducing conditions. So say we're using sodium cyanoborohydride. Again, typically these borane reagents will have a cyanoligand on the boron. We just switched the metal here, sodium cyanoborohydride. Again, in the presence of trifluoroacetic acid, that brings the pH about 4, and again we'll use THF as our solvent. So I'll go ahead and draw the product out, and then we'll consider the mechanism. So again, we started with a secondary amine, and so now we're ending up with a tertiary amine. So we can count the ligands on nitrogen. 1, 2, 3. That gives us our tertiary amine. So again, starting from secondary, we get tertiary. But what is the mechanism of how this happens? So let's consider that. Because that's going to really be important for the chemistry of enamines that we're going to study later on. So there's our enamine, and I want to draw a resonance form. So there's our resonance arrow. So we have a negative charge here, negative charge here at what is the alpha carbon, a positive charge on the nitrogen. So this reactivity is matched with the reagents that are present. So we have an acid, which is going to react here, and then the hydride, which is going to react there. So let's go ahead and show the acid-base reaction first. So this is a protonation. So we end up with the conjugate base of that acid. We've matched the charges, so plus, minus. Let me show you a resonance form here. So resonance arrow. So this helps us understand why the hydride is delivered there. So hydride is delivered. And we end up with our tertiary amine. So you can see we have 1, 2, 3 ligands on nitrogen, so that makes it a tertiary amine. So the reductive amination strategy is pretty powerful for making higher order amines, and by higher order I just mean how we're classifying. So we go from secondary to tertiary. And overall, this process, reductive amination, is important if you're going on to take biochemistry, because that's how enzymes work, is through a reductive amination process for those type of reactions. So I want to finish off this screencast with showing a couple more addition reactions to aldehydes and ketones that are unique and involve the installation of nitrogen So aldehyde and ketone, addition of cyanide specifically. And so let's look at, say, propanone. And if we were going to treat propanone with HCN, so hydrogen cyanide, what's going to happen is that first an acid-base reaction will transpire. So we're going to protonate the aldehyde carbonyl So we have this protonated carbonyl, then we have the cyanide anion. So we can see that this is going to attack this carbon and then push electrons up onto the oxygen. So this compound, this functional group, is called a cyanohydrin. So we have a carbon bearing an alcohol and a nitrile. And so this functional group cyanohydrin is useful because we can do a lot of transformations with it. So let's look at a couple in this space here. So one, we can do hydrolysis. So if we treat with strong mineral acid HCl and water and heat, what that is going to do is take this functional group here. Again, this carbon is at an oxidation state of 3. Again, you count the number of bonds to nitrogen, you have 1, 2, 3. It's going to transform that nitrile into a carboxylic acid. And if you still count what this means, you're still at an oxidation state of 3. So you're not doing an oxidation or reduction, you're just doing a transformation of nitrile to acid. So this is so there's our alpha carbon, alpha hydroxy acid. So we can do a similar reaction. We'll call it hydrolysis dehydration. Where in this case we're going to use sulfuric acid and heat, which is going to transform this into the acid and then do a dehydration across the alpha beta carbons. So there's alpha, there's beta. And this functional group here, this alpha beta unsaturation, is going to be useful to us in Module 3 when we start looking at the formation of carbon-carbon bonds and the addition of nucleophiles to the beta position. So one other reaction we can do with these cyanohydrins is a reduction. So we can take a cyanohydrin, treat it with lithium, aluminum hydride, and THF, then do an aqueous workup. We're at oxidation state 3. And what a hydride reducing agent will do is reduce that down to an oxidation state of 1 with retention of the amine. And so now this is an amino alcohol. So we have the amine, we have an alcohol. They're in a 1-2 relationship to one another. So again, nitrile at oxidation state 3, hydride reduction, we've added 1-2 hydrogens. So now this carbon we count, we only have 1 bond, so we're in an oxidation state of 1 here. So in this screencast, we've looked at the formation of amines and then their reduction in the reductive amination strategy. And then we've looked at a special case of cyanide addition to aldehydes and ketones to form cyanohydrins, and then 3 reactions of those cyanohydrins.